Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on August 5th, 2025, just 2 days ago. This paper shows how reinforcement learning can nearly double the success rate of an AI agent on complex software engineering tasks, boosting it from 20% to 39%. The paper is titled, Training Long Context, Multi-Turn Software Engineering Agents with Reinforcement Learning. And the implications for building more capable autonomous agents are really significant. The core idea is applying reinforcement learning, which is a training method where an agent learns by trial and error, to teach language models how to handle these complex, multi-step software problems, which require a back and forth with their environment. Alright, and this chart really visualizes that improvement over the course of training. The solid blue line tracks the pass at 1 score. That's the agent's success rate on its very first attempt, and you can see it climb from that initial 20% baseline to just over 40% by the end. The orange line shows the pass at 10 score, its success rate with 10 attempts, which is significantly higher. This large gap suggests that even better performance is possible, for example, by adding a re-ranking mechanism to pick the best solution. So, to really appreciate why that performance jump is so significant, this diagram illustrates the core challenge. At the top, we see a simple bandit-style problem, like math. The model gets one question, gives a single answer, and that's it. One and done. But the bottom part shows a software engineering task. This is framed as a partially observable Markov decision process, a formal way to describe a multi-step interaction where the agent doesn't see everything at once. Here, the agent goes back and forth with its environment, adjusting its approach based on feedback before getting a reward. This table then details that progression, showing the numbers behind the agent's improvement. The base model, QN 2.572b Instruct, starts at just over 11% on the SWE Bench verified benchmark. After an initial phase of rejection fine-tuning, which is a method to get the model to follow instructions better, that score nearly doubles to 20%. Then, the 2 stages of reinforcement learning push it all the way to 39%, making it competitive with other leading open-weight models like DeepSeek V3. And this table puts that 39% score into the broader context of other specialized software engineering agents. It compares their final model against others on the SWE Bench verified benchmark. The key takeaway is in this final column. Teacher distillation. Notice that their agent at the top achieves its strong result without it. This is a significant accomplishment, as many other high-performing agents listed here do rely on that technique, which involves learning from a more powerful, often proprietary, teacher model. Now, this diagram lays out the complete, multi-stage pipeline they built to achieve those results. It's a synchronous loop, meaning each step has to finish before the next one starts. The process begins at the top with the inference servers, which are GPU-heavy, generating the agent's attempts. Next, the CPU-heavy stages handle rollout generation and the verification process. This is where the agent's code is actually run and tested. Finally, after preparing the dataset from these runs, the model is trained on the GPUs, and the updated model checkpoints are sent back to the top to start a new iteration. So to wrap up, this work shows a viable path for training capable agents on complex, multi-turn tasks using reinforcement learning. It's a significant step for open-weight models, achieving strong results without relying on a teacher model. That's it for this episode.